students, welcome to Sunil's tutorial. I'm Sunil Merwani and today we'll be doing interference of light. Let's see this. Let's see theory of interference band. Let's consider that I have two sources A and B at a distance of d from each other. Let us assume O is the midpoint of AB, right? Let us assume that you have a screen at a distance of d from the slit, right? Now, if I were to project straight lines onto the screen, then these will be the straight lines projected onto the screen at point N, P and M. There is a point Q which is at a distance of x from P. I want to know what will be the point. Will this point Q be a bright point or a dark point? Fine. Join AQ and join BQ. Right? Now, let's see this first. Let's write this down. Consider, let's write the explanation of the diagram down. Consider two monochromatic linear sources A and B separated by a distance of d. Two monochromatic linear sources A and B separated by a distance d. Right, let's assume that d is the distance between them, which produce interference pattern on the screen, which produce interference pattern on the screen, which produce interference pattern on the screen at a distance, placed at a distance d from the source. So this is the distance between the two slits, this is the distance of the screen, right? Let us assume that lambda is the wavelength Let's assume lambda is the wavelength of the light source emitted, from each source. Right? Now, let us assume that from A and B, let us draw perpendiculars AM and BN on the screen, right? So let's assume that AM, BN and OP are perpendiculars from the source drawn on the screen. Fine. Now, the interference pattern that would be produced on the screen would consist of alternate bright and dark point. Now let us consider point Q on the screen at a distance of x from P. Consider a point Q on the screen at a distance of x from P. Right? Now if Q is at a distance of x, now I want to find out whether this is going to be a bright point or dark point. Now for that, what I'll do is first I'll join AQ and BQ. Right? In that case, from the figure it is very clear that the path difference of the light waves arriving at point Q, path difference of light waves arriving at Q will be, the path difference is going to be nothing but BQ minus AQ. That is going to be my path difference. If I subtract BQ minus AQ, that will give me the path difference. Now, first let's consider for a bright point. We had seen the condition for a constructive interference. For bright point, we had said that the path difference should be a integral multiple of lambda, right? Now, point Q will be a bright point. Point Q will be a bright point if the path difference is equal to, is an integral multiple of lambda, is an integral multiple of lambda, right? That means therefore I should say that for bright point BQ minus AQ should be equal to n lambda, where n can be any number from 0 to infinity, right? Okay. Now for dark point, we had also done this. For point Q will be dark. If the path difference is half, is equal to the odd multiple of half wavelength, is equal to odd multiple of half wavelength. That means for dark point, the BQ minus AQ path difference should be equal to odd multiple of half wavelength, n minus 1 by 2 lambda, right? Where n here will be any number from 1 to infinity, right? Now, from the figure I can say from triangle AMQ. In triangle AMQ, I can say that AQ square is equal to AM square plus MQ square. Fine, do we get this simpler? Next, so in that case, I can say that AQ square is AM square can be written as B square plus MQ. Now MQ is going to be nothing but X minus, now guys, let's try to understand this. Look at the figure. This whole distance is D, guys. That means the distance between PM will be D by 2, because I've said that P and O are the midpoints, and this distance will also be equal to D by 2. That means I can say MQ is X minus D by 2. This total distance, that is PQ minus PM, will give you QM. PQ minus PM will give you QM. So QM can be written as, guys, QM can be written as X minus D upon 2 the whole square. Fine, do we get this thing here? Now similarly I can say that from triangle BQN, from triangle BQN I can say that BQ square is equal to BN square plus NQ square. So this is going to be D square plus NQ is going to be nothing but NP plus PQ, right? Which is going to be nothing but X plus D upon 2 the whole square, right? Now I can say subtract the two equations. Therefore, what will be BQ square minus AQ square? BQ square minus AQ square will be D square plus X plus D by 2 the whole square minus D square minus X minus D by 2 the whole square. I'm subtracting the two equations. Plus D square minus D square gets cancelled. This is going to be nothing but X square plus 2AB, X into D by 2 plus d square by 4 minus x square minus into minus plus 2x d by 2 minus d square by 4. I'm expanding using the formula a plus b the whole square and a minus b the whole square. In which case x square gets cancelled, d square by 4 and d square by 4 gets cancelled, 2 and 2 gets cancelled, 2 and 2 gets cancelled. So in which case I'll get path difference, no, bq square minus aq square is 2xd, right? So now I can say that now bq square minus aq square is nothing but in the form a square minus b square, which can be written as a plus b, a minus b. This can be written as bq minus aq into bq plus aq is 2xd, right? Once I have this, then I can therefore say that bq minus aq is nothing but 2xd upon bq plus aq, right? But x and d are very small. Since x and d are very small as compared to d, therefore I can say that bq will be approximately equal to aq, will be approximately equal to d, therefore bq plus aq will be equal to 2d. Hence I can say that bq minus aq is 2xd upon 2d. 2 and 2 gets cancelled, therefore I'll get bq minus aq is xd by d. So my path difference is going to be equal to xd by d. Now substitute this equation of path difference for bright point. Substitute this equation of path difference for bright point. Now for bright point we had said that bq minus aq is equal to n lambda, therefore I can say that n lambda is equal to xd by d, right? Therefore I can say that this is going to be my equation for bright point, where n can be any number from 0 to infinity, right? And similarly, if I substitute this equation of path difference for dark point, this equation of path difference for dark point, I can say that bq minus aq is equal to path difference for dark point. We had said is odd multiple of half the wavelength, right? So in that case I can say xd by d is n minus 1 by 2 lambda. So that is going to be my condition for bright point and dark point on either side, right? Do you get this thing here? So that's how I find out bright point and dark point. Fine. Now the distance between two consecutive bright or dark points is called as bandwidth or fringe width. The distance between two consecutive bright or dark points is called bandwidth or fringe width, right? Now once I know what is bandwidth or fringe width, I can say that let us assume that let xn be the distance of the nth bright band, be the distance of nth bright band, right? And let xn plus 1 be the distance of the next bright band. Be the distance of next bright band from T. Right? So in that case, by definition, bandwidth or fringe width capital X can be written as bandwidth is xn plus 1 minus xn. It is the distance between two consecutive bright or dark bands, right? But we have derived that for a bright band, we have derived that xn is equal to xn d by d is equal to n lambda. That means xn is equal to n lambda d by d. Similarly, I can say that xn plus 1 is equal to n plus 1 lambda d by d. Therefore, fringe width is going to be but fringe width is xn plus 1 minus xn, so that is n plus 1 lambda d by d minus n lambda d by d. Lambda d by d gets cancelled, common, so I'll get n plus 1 minus n, take lambda d by d common, so I'll get this fringe width is equal to lambda d by d. Right, do we get this thing clear? So the fringe width or the bandwidth between two consecutive bright bands is lambda d by d. We say therefore fringe width between two consecutive bright bands is lambda d by d. Fine. Now let's find out the fringe width for a dark band. Right? I can say for a dark band, I can say that for a dark band we have derived that xd by d is n minus 1 by 2 lambda. Therefore, I can say xn is equal to n minus 1 by 2 lambda d by d. Right? Similarly, xn plus 1 is n plus 1 minus 1 by 2 lambda d by d, but by definition fringe width is the distance between two consecutive bright or dark bands, so xn plus 1 minus xn, fringe width is going to be xn plus 1 minus xn, so I can therefore say that fringe width is going to be x plus 1 minus 1 by 2 lambda d by d minus n minus 1 by 2 lambda d by d, right? In which case I can take lambda d by d common, so I'll get n plus 1 minus 1 by 2 minus n plus 1 by 2 lambda d by d. N and n gets cancelled, 1 by 2 gets cancelled, so fringe width is equal to lambda d by d. That means the fringe width for two consecutive dark bands is also lambda d by d. I can say that the fringe width for two consecutive dark bands is also lambda d by d. So for bright bands it is lambda d by d, and for dark bands also it is lambda d by d. Thus I can say that fringe width, irrespective of whether it is a bright or a dark band, is going to be lambda d by d, It also proves to us that the dark bands and the bright bands are alternatively and equally spaced between each other, right? I can say therefore the distance between two consecutive bright bands is equal to the distance between two consecutive dark bands, because the fringe width has come out same in both the cases. Thus I can say that bright and dark bands are equally and alternatively spaced. Thus bright and dark bands are equally and alternatively spaced. Hence, I can say that the bandwidth x is given by the formula lambda d by d. That is going to be my fringe width. Fine, do we get this thing here? So do we understand how do we find out the fringe width in Young's double slit experiment? Now the same experiment was done by another scientist called as Fresnel. Let's see Fresnel's experiment. His experiment is called as the biprism experiment. He derived or he came up with another method of getting two coherent sources. Instead of using a cardboard with two slits in it, he used a biprism, or he used a prism to get two sources of light. What he did was, he used a prism. Now you have source of light somewhere here, right? From here the source of light, from source of light you have rays of light that will go on to the prism, right? These are the source. From source the rays of light will go to the prism. Now from prism, since here they are towards the corner, they will hardly get refracted, they'll move straight, right? These will move as if they are being refracted from here, right? Similarly, this is going to move straight. This they will produce a bright spot on the screen. Right? So this is as good as two sources of light being focused onto the biprism, right? So these are the two virtual sources that will be focused onto the biprism. This is going to be the Amra cone of the biprism, where you will get a dark band. Right? This is your straight line that will move ahead. Center. Right? So this is your biprism experiment. Find the this thing here, where you have, this is your biprism, right? Here you are going to have a micrometer screw gauge, right? This is going to be a micrometer screw gauge. On the micrometer screw gauge, you have the eyepiece that is kept, and this is how the rays of light will move. This is going to move from here this way. This will move this cross, and you will have the image that is going to be formed. Right? Now, Young had demonstrated the phenomena of interference, but it was doubted whether the fringes were formed due to interference or not. Now this doubt was removed with the help of Fresnel's biprism experiment. Now the most important condition for steady state interference pattern that we had discussed was that the two sources of light should be coherent. That is, the phase difference between them should be zero. Now Fresnel used in his experiment a biprism to get coherent sources of light. So let's see Fresnel's experiment. Fresnel used a biprism to obtain coherent sources. Right? He used the biprism was a prism having a very large refracting angle of 179 degree. Was a prism having a very large refracting angle of 179 degrees. Fine, do we get this thing here? Now, the ray diagram, this is the ray diagram for Fresnel's biprism experiment. You had a narrow slit S by a narrow vertical slit S was placed or is illuminated by a source right? In that case, the biprism B, this is your biprism B. The biprism B is placed close to the slit. Biprism B is placed close to the slit. Right? Now, the refracting edges of the biprism, the refracting edge AC of the biprism is kept parallel to the slit. So this is that refracting edge AC. The refracting edge is kept parallel to the slit. Right? Once the refracting edge is kept parallel to the slit, then I can say that you would have refraction taking place and you would get an interference pattern. The monochromatic source of light from S would be incident on the biprism. Monochromatic source of light from biprism, from monochromatic source of light from slit S would be incident on biprism and the ray would appear to come from two virtual sources S1 and S2 of the slit, and the ray would appear to come from two virtual sources S1 and S2 of the slit. Right? Now, since the two virtual sources act as coherent sources, and these two virtual sources would act as coherent sources of light, since they have been derived from the same source, the two virtual sources sources would act as coherent sources. So that's how you got coherent sources using a biprism, right? The light from these coherent sources would interfere and the shaded region would superimpose with each other and which could be seen through the eyepiece. The light from these two coherent sources would interfere with each other, and that's how you would get an interference pattern, right? So that's your ray diagram for Fresnel's biprism experiment, right? Now let us see the experimental arrangement for Fresnel's biprism experiment. Let's see the experimental arrangement for Fresnel's biprism experiment, right? Where you have a stand on which you have a slit that is placed, right? Then you have on another stand on which you have the biprism placed, right? And then you have micrometer screw gauge on which the eyepiece is placed, and you also have a convex lens that could be placed between the biprism and the eyepiece, a double convex lens, and then you have the micrometer screw gauge on which your eyepiece is placed. Right? And this is placed on the micrometer screw gauge. The entire arrangement is then placed on a stand, on a base where the stands can be moved. Right? So this is your slit, biprism, convex lens and eyepiece. Fine, do we get this thing here? This is your experimental arrangement for Fresnel's biprism experiment, right? This particular bench is called as your optic bench. So on an optic bench you have 4 stands on which you have these 4 things placed, right? Okay, let's see this. I can say that Fresnel's biprism experiment, the optic bench is about 1.5 meter in length and is marked along the length. Fine, do we get this thing here? Next, once you have this, I can say the slit, the biprism and the micrometer eyepiece are carried on adjustable stands. These are those adjustable stands. The slit, biprism and eyepiece, micrometer eyepiece are carried on adjustable stands which are mounted on the optical bench. Mounted on the optical bench. Right? Another stand is mounted on the optical bench between the biprism and the eyepiece on which a convex lens is placed. another stand is mounted between the biprism and eyepiece. Another stand is mounted between the biprism and eyepiece on which the convex lens is placed. Right? Convex lens is placed. Now the slit and the biprism can be also rotated about the horizontal axis. The slit and biprism can also be rotated about horizontal axis. Fine. Now the slit, biprism and the eyepiece are kept at the same height. Slit, biprism and eyepiece initially or at the start of the experiment are kept at same height. Right? Once you have this, the slit is made narrow enough and is illuminated by a monochromatic source of light. The slit is kept narrow enough and illuminated by a monochromatic source. Right? The stand between the slit and the biprism is kept close to the slit and is kept vertical. The stand stands having the slit, and biprism are kept close together, and the slit is kept vertical. Is kept vertical. Right? Now, the biprism is then slowly rotated along the horizontal axis so that the refracting edge is parallel to the slit. The biprism is slowly rotated about horizontal axis so as to make the refracting edge parallel to the slit. This is how you actually do Fresnel's biprism experiment. Fine, do we get this thing here? Now, let's see in Fresnel's biprism experiment, how do I determine the wavelength of light? Determination of wavelength. Right? Straightforward. The wavelength of monochromatic light can be determined by using Young's double slit experiment. I can say that lambda is going to be xd by d. This is how I will determine the wavelength, where x is the bandwidth X is going to be the bandwidth, D is going to be the distance between two coherent sources produced by the biprism. Distance between two coherent sources produced by biprism, and D is the distance between the source and the screen. Distance between source and screen. That's how I find out the wavelength in Fresnel's biprism experiment. Next, how would I determine determination of or measurement of D? Measurement of D. How do I find out the distance between the source and the screen? In this experiment, it is the screen is replaced by a micrometer eyepiece, and the two coherent sources are formed in the plane of the slit. Hence, the D is the distance between the slit and the distance between the slit and the eyepiece can be easily measured, and that will be your distance. And that is not contrary to what people generally believe. It is the distance between the biprism and the eyepiece. No, it is not the distance between the biprism and the eyepiece. Right? So D is actually the distance. I can say that in this experiment, the screen is replaced by eyepiece, and the two virtual sources are formed in the plane of the slit, are formed in the plane of the slit, right? Hence, D is the distance between the slit and the eyepiece. Hence, D is the distance between the slit and eyepiece, which can be easily measured by a scale, by the scale marked on the optic bench. That's how you would measure D in the case of biprism experiment. Next, how would you measure the bandwidth? How would I measure the bandwidth in the case of biprism experiment? Now, what is bandwidth? Bandwidth is the distance between two consecutive bright or dark bands, right? This can be easily measured by using the micrometer eyepiece. Bandwidth is the distance between two consecutive bright or dark bands and can be easily measured by using the micrometer eyepiece. How? Right? The eyepiece is first adjusted such that the vertical cross wire coincides with the first bright band. Right? At the end of the interference pattern. See. How do I do this? I'll say that the eyepiece is first adjusted such that the vertical cross wire I hope what you all know what is the meaning of crossfire. Now, when you are shooting someone, you have a plus sign. When you see from the micrometer screw gauge, you have this plus sign. That's called as a crossfire. This is your vertical crossfire. This is your horizontal crossfire. So that the vertical crossfire coincides with the bright band. Vertical crossfire coincides with the bright band. Coincides with the bright band at one end of the interference pattern. One end of the interference pattern. And the micrometer reading is noted. Right? Next, the micrometer screw is then rotated so that the vertical crossfire coincides with each successive bright band. The micrometer screw is rotated so that its vertical crossfire coincides with each successive bright band. And every time the micrometer reading is noted. The micrometer reading is noted. Right? And that's how let's consider if x1, x2, x3 and so on are the readings for successive bright bands, then the average value of x2 minus x1, x3 minus x2 and so on gives x. That's how I get the bandwidth. Right? Do we get this thing here? Okay, we'll stop this here for the day. Thank you very much.